All right, so we're going to get started today with the flip-flop and other basic memory devices. And we're going to start with the device called the SR latch. I don't think we have gotten to the SR latches yet in this class. All right, so today's going to be, so this is kind of like a transition of this class from computation and how things are represented to the other aspect of inside what is inside the processor. Particularly, we're going to get to the part where, oh, so how does a computer remember things? How does it update things, and so on? So this is a transition. So the first thing we look at this and go like, okay, this entire module is called the Varnum architecture and memory. So exactly what is Varnum? Sounds like a name to me. Sounds like a Austrian slash German name, which it is. So we're going to take a quick look at what is Varnum. Okay, so which is the last name of the person who came up with the architecture that we are now using. So his name is John Varnum, um, and he originated from Hungarian. Okay, so I was wrong. It's not German nor Austrian, but he is one of the kind of really important polymath of this entire century, of the 20th century. His contribution is not only to computer science. So if you read about what his quote unquote occupation, he's a mathematician, he's a physicist, he's a computer scientist, he's also an engineer. Okay, those are his titles. But when you look at what his contribution were back when he was around, it includes the following. Okay, it includes mathematics, physics, economics, computing, statistics. Okay, now there are people like me, which I would say, tech of all trade, but master of none, right? But he is a master of everything. During his time, you ask any physicist, including Albert Einstein, which overlapped with John Barnum, they will all say, "Oh, he's a brilliant guy." You ask any economist, they will say he's a brilliant guy. You ask any mathematician, they will say he's a brilliant guy. Okay, now that is rare. Okay, it is not common that you will find a polymath that is excelling in every single field. So now the question is, okay, he does a lot of things in quantum mechanics. He does a lot of things in game theory and whatnot. Those are all kind of niche areas. They're not really kind of mainstream, in each of those particular area. He passed away when he was relatively young. Okay, so when you look at his age when he passed, so he was born 1903. He passed away when he was only 53 years old. I can understand how young that age is because I'm already 57. So he passed away 4 years ago in my own age. So in my scale, that's pretty young. Okay, but you guys can say, but Tech, you are actually kind of old, which I'm okay with that too. So anyway, that's his background. So now the question is, if he was not around, if he did not come up with what we now call the Von architecture, what would this world be if he was not around? Okay, so the interesting thing is the world actually will be entirely different compared to what it is now. So let's take a look at a computer prior to the John von Neumann architecture. In the past, I always have to kind of look for that and whatnot. But now with AI, I can just search, right? I can just ask, okay, what is an example of a computer prior to the von Neumann architecture? Okay, there we go. And it would even have pictures, okay, the ENIAC, okay. All right, so let's take a look at the ENIAC because all I really want to do is to take a look at the picture itself like this. Okay. And what you can see is a really big switchboard on this side. The switchboard is how it is programmed. All of these little dots here that you see on the left hand side, they are all electrical contact points. The behavior or quote unquote programming, which is not the same as what we see as a program these days, the behavior or the specification of the behavior of a computer is entirely determined by the wiring, as in physical wiring, as in wires that you can look at and disconnect and reconnect. Okay, so that means if the program is not doing what you think it should be doing, like it's not doing the computation correctly, you have to go through that massive wiring to figure out, okay, so where did I make a mistake? Okay, and how do I fix it, right? So you have to unwind all the wiring, all the ones that are wrong anyway, but because they are layered, right? So that means, just to fix one little problem, sometimes you have to unwind a whole bunch just to get to the one that was wrong. Okay, so that's basically how a computer was quote unquote programmed, back in those days before the von Neumann architecture. Yes. Um. Well, let's take a look. Well, there were several machines, invented during World War II. I believe the ENIAC may also be a product of World War II, but it might have a very specialized application, which I think was the computation of the trajectory of the projectile coming out of a naval gun. I could be wrong, okay? Yeah, but I think that's why we have the ENIAC computer. Um, and we can take a quick look. I'm curious. Now that you asked the question, I blame it on you. No, this is actually general purpose digital computer completed in 1945, so it does fall into the time frame ish, in World War II. Um, but it's general purpose, which means it doesn't have a specific, purpose. But the other one, the one that Turing worked on, that was for deciphering the encrypted communication from German to German, communication. Um, and if you watch the movie, which is partially accurate, um, it is actually quite an invention because they were able to, the machine, okay, was able to decrypt German enemy, communication before the enemy, because the enemy was using a manual process, right? So one guy would be listening to the radio and go like, okay, let's say a four, no, a T, M, and all the actual transmission, and then the other person would be typing that thing through the decrypting machine. So it is a manual process, and sometimes they will make a mistake, and nothing makes sense. Okay, they go like, okay, can you retransmit? And then the British will be snickling and go like, we got it the first time. Yeah, I'm pretty sure that's a very satisfying feeling when you are decrypting the enemy transmission faster than your enemy could do it without any mistakes. And then you just listen into your enemy going like, oh wait, I didn't quite get the message. I mistyped the key. Can you retransmit? You go like, really? Anyway, getting back to the contribution of the von Neumann architecture. Okay, so with that type of programming, okay, do you have any reason to shrink transistors down to nanometers? You would have absolutely no reason to do it, right? Because the limitation is going to be, okay, what is the smallest connector I can make so that I can still manually reconnect those connectors? Okay, so let's just say that you have really fine tweezers and whatnot, and you can shrink it all the way down to, we'll just make an assumption here, 1 millimeter. That's pretty small for something that requires hand tools, right? So that means we are not going to shrink transistors beyond 1 millimeter, which also means that the computational speed is going to be very limited, and the complexity of what we can specify is also going to be very limited because everything is hardwired. How complex of a program can you specify when the entire behavior of the program is done by hard wires? Okay, So if that was the case, if John Barnum did not come up with the idea that he came up with, which I'll explain later, we would still have computers that would take up entire rooms, okay, and it would take a lot of electricity. So you go like, okay, so what is the big deal? Okay, we just have bigger computers, okay. So let me ask you this question: if you compare an airplane from World War I, okay, the biplanes, okay, the Red Baron and all those, good old days, okay, and you compare that to the top of the line F-35 today, okay, you go like, well, that's a huge difference, okay, because those biplanes or triplanes have a top speed of about 70 miles per hour, okay, which turns out also to be the top speed of my car. Yes, I have a car that has a top speed of 70 miles per hour because it's a 40-year-old car. And when it was brand new 40 years ago, it had 63 horsepower. So over the decades, I'm sure a few horses have escaped or died in the process. So anyway, 70 miles per hour, okay, not respectable in any way. And the F-35, I think it's about 70, 70 times, that speed. Um, we can look it up. I looked it up before, but I'm gonna look it up again. Top speed. So Mach 1.6, which is, what, 1200 miles per hour. Okay, so look at the scale. So we are looking at 70 miles per hour against 1200 you know uh, miles per hour. Sounds huge, right? Because let's just round up things a little bit, just so that it's easy to compare. So let's just say that we're looking at 70 versus 1400, and if my math is correct, it is a 20x change. Is that correct? 20 times 70 is 1400. Okay, 2000%. Okay, that's pretty big as a difference. So we look at the 2000 20x, and we go like, okay, how does that compare to the progress of semiconductors? In other words, all the modern technology with computers and whatnot. Okay, so let's make that comparison. What is Moore's law? What does it say? Yep, it is about the doubling of density of transistors, which is actually kind of the other way around. It's measuring the how long does it take to halve the size of a transistor? But roughly it is the doubling the density, which also kind of double the speed because the smaller the transistor, the faster it can transition, and the faster we can do computation. Okay, so Moore's law says we double the density of transistors every. It used to be 18 months, but now it's slower. 2 years. So we double every 2 years. We go like, well, that doesn't seem really fast to me. But it is exponential, exactly. So now we look at 32, okay, and we'll even round this up to 30. 20, we'll round it up to 32 because 32 is a nice power of 2. So how many times do you have to go through the Moore cycle in order to get a 32x of performance? So that's just 2 to the power of what is 32? Come on, you guys should know this. 2 to the power of x is 32. What is that x? It's 5. Okay? Takes 5 cycles. Okay? So it takes 5 more cycle to do it. And using a very conservative estimate, one cycle is 2 years. So that's 10 years. Okay? In 10 years, okay, according to Moore's law, electronics or anything that depends on electronics would be 10x or excuse me, 32x the performance. Okay? So this is what 2025, right? So that means compared to 2015, our computational hardware today has about 32x the performance. Now, it's not just the speed either, okay? Communication, storage, computation, everything is 32x compared to 10 years ago. Are we good with that? All right. Um, how long did it take for the triplanes and biplanes to progress to the F-30, 35, which is top of the line today? So we are looking at the duration of World War One to 2025. So we are talking about 1914-ish to 2025. Let's round up again, okay? Because I like round numbers. Let's just say World War One, lasts until 1925, okay? An entire century, okay? What took an entire century and lots of money, because the military has money and they like to spend money, and when we are at war, we spend every last penny to make things go faster, right? So it took 100 years to get this 20x, with entire countries throwing every penny, every resource to do this, okay? As opposed to 10 years, less than 10 years, with only commercial companies like, oh, okay, we have a competition, Intel versus AMD, but that's about it. Okay, in terms of competition, that's it. AMD versus Intel, or the fab houses. Okay, there are only a few in the entire world. Nvidia is kind of like I consider Nvidia an afterthought for many reasons, but we're not going to get into that. Okay, so we are looking at 10 years versus an entire century. That is made possible only because we are not using wiring to program the computers. Because if we were still using wiring to control or to specify the behavior of computer, there would have been no reason, even if technically we can do it, there would have been no reason to shrink transistors beyond a certain practical size. Is that okay? So without that progress, without the Moore's law in place, and let's just say that we start with the ENIAC computer and we do the kind of usual progress, we would still be using computers about the size of a refrigerator, but it has less processing power than your watch. You turn on the computer, everything dims. And then you hear the generator goes back up. It's like that. That is what we are dealing with. Okay. I want to convey this not only because it is fascinating to me, but because it is actually important in your future. Why is it important from your perspective? Not even looking at it from the perspective of, oh, this is interesting historical fact. No, we are not seeing this as interesting historical fact. Why is this important to you? Okay, well, it gives you the idea that if Moore's law continue, by the time you graduate with a bachelor's degree from a CSU or a UC, everything will be at least 2x compared to what we have today. Does that make sense? Because if you're in this class now, it will take you at least 2 more years to get your bachelor's degree in computer science. Those 2 years is already one Moore's law cycle. Everything is going to double. So that means all the AI hardware is going to at least double. And you guys would say, but there's an energy wall, okay? Because if they're using so much energy, there's only so much computation you can do. But guess what? The energy efficiency is also doubling. So you are guaranteed at least 2x just because of the efficiency gain. Storage is going to double. Okay, the amount of memory of those AI chips is also going to double, which means if we are looking at, let's just say, 200 billion parameter LLMs today, in 2 years, it'll be doubled easily. Are we are we starting to understand the concept of scaling? All right. So that is why it is important to understand, Moore's law, and also, indirectly understanding why John Vonneman's, contribution to computer science. Because without his contribution, we'll be looking at a really slow progress, just like airplanes. Are we good so far? All right. So now the next question is, okay, now that we understand, his contribution, what makes it possible? Okay, what does it actually entails? What is the what is the von Neumann architecture? Well, back in those days, okay, let me go back to the ENIAC computer. The ENIAC computer already has memory in it. Because if the purpose of the computer is to do computation, for those of you who are currently taking calculus, you understand that some of the equations they do not have a closed form. So that means you don't have a clean and nice and simple and elegant way and say, oh, the integration of this is this, or the differentiation of this is this over here. Some of those things are really messy, and the only way to do integration is really the long way, which is a whole lot of calculations. Okay, so in order to do those calculations, you also need memory because you need a variable to store, okay, what is the total area under this curve up to this point, okay, in two-dimensional integration. So you need memory already. So John Varnum's idea was, oh, in addition of using memory to store the data that we are processing and to store partial results that we are adding and multiplying and whatnot, we'll also use memory to store the instructions to tell the computer what it needs to do. No, no, just instructions. We are talking about really simple stuff. Okay, but the change is simply to go from massive, crazy wiring to some kind of construct inside the memory system of a computer that removes the physical limitation of what you need to do to change the behavior of the computer. So that alone allow computers or transistors shrinking and shrinking and shrinking, and we'll still be able to specify the behavior of the computer. Does that make sense? Because what used to be something that you have to do manually, which is limited by how small of a tweezers, how small of a pairs of tweezers we can make, to simply, oh, okay, we'll just kind of change the memory of the computer to change the behavior of the computer. So that's a huge change. Okay. So now the next question is, okay, well then how does a computer remember anything? Because it sounds like, you know, the whole thing is hinging on the computers being able to store and remember things. So that's going to be kind of this is the backdrop of today's lecture is, how does a computer actually remember anything? Okay, because that is pivotal in order for the von Neumann architecture to function. Are we good so far in terms of just establishing the context of what we're going to talk about today? All right, cool, excellent. So we are going to, let me see if I can use the tablet today. Some days, it doesn't want to cooperate, and other days it is okay. So we'll see if today is one of the better days. So go to Files, go to Notes, go to 310 Monday, Wednesday, and go to screen share. Looks like everything is up and running, so we'll see. We'll take a look here. Supernote. Hey, it works. Okay. I'm still trying to figure out the pattern because on certain days in a particular classroom it doesn't like to work, but I still haven't figured out the pattern of why that is the case. Now I need to go find my stylus, which I cannot find. Without the stylus, this is not gonna work. Uh, oh no, it's here. It's here. I can feel it. It's just a compartment inside here. Yep. Whew. Okay. Too many pockets. This is why my desk is a mess. Because if I keep putting things into drawers and containers and whatnot, it just makes things more difficult to find. That's my excuse of keeping my desk messy. All right. So I'm going to present a circuit to you. And later on, we can play with it. Okay, so it has two NAND gates, two input pins, which I label SR, which is also why it is called SR latch. It has two output pins, which I will label Q, which for some reason is the label that we use, to say, oh, this is the output of a transistor. So this goes here, this goes here. This goes to one input of the two input NAND gate. This goes to the one of the inputs of the other NAND gate. So right now we go like, oh, okay, that doesn't sound too bad. So now we go like, wait, this is the fun part of a SR latch. The output of one NAND gate goes to the input of the other NAND gate and vice versa. So we go like this, okay? Huh, nope. We have not seen a circuit where the output goes back to the input. And you can also see this as a weird crisscrossing loop of some kind, right? Because you can see how this goes here, this goes back here, and then this goes all the way back here again. Oh, it's kind of like a figure eight, infinite loop. So you would think, man, this is going to be hard to figure out, right? That's what I thought too. So you're not alone. We'll call this N1, we'll call this N2, just so that we can refer to the individual NAND gates by their names. So go like, whoa, what is this? I mean, this is pretty mysterious. Okay, how do we figure out the behavior of this little circuit here? So what we'll do is we are going to analyze the circuit using what I would call propagation analysis. Okay, so propagation analysis depends on propagational delay. So I'm going to put this on the next slide and then come back to this slide, after we explain this. So we already know what a NAND gate looks like in terms of transistors, because guess what? When did we talk about that? Day one of this semester. Okay. Now, if you cannot remember, what it looks like, that's fine. Okay. I'm not counting on you guys remembering all that. So I'm going to draw the circuit here. Okay. You don't have to draw that. Okay. This is just me illustrating things. Okay. So you don't have to draw this if you don't want to. Okay. I don't even care, where the gates are connected to, because it's not the important part of this discussion. The important part of this discussion is, if I were to take a look at just this portion here, what does it look like? In other words, in a electronic circuit, what is this symbol? Has anyone taken an electronics class from electronic technology or a class in physics that talks about electricity? Hmm? It is. It's not a switch. It is called a capacitor. Okay, it's a capacitor, which means, it is a device to store a charge, kind of like a battery, but not exactly the same as a battery in terms of the chemistry. But it is kind of like a really, really fast and really, really small battery. Okay, so that means you can charge it up, you can discharge, you can charge it up, you can discharge. But when we look at a wire, okay, if we just look at the wire here, ideally, okay, from the computer science perspective, and even from the computer engineering perspective, a wire is always a perfect conductor in every way. But in reality, we have this little thing called physics that throws wrenches into ideal assumptions. Okay, so physics says, guess what? That copper wire, in your circuit board, on your circuit board, or inside the processor, it is not perfect in the sense that, oh, whatever voltage you present on one side is immediately on the other side. So every wire has two internal components. One is a resistive component to it, and the other one is a inductive component to it. So now you're looking at, if you just look at this little subpart here, you're looking at something that is, oh man, this is terrible, because now you have to learn about capacitance, you have to learn about inductance and resistance in order to figure out, When we make a change on this side here, how long does it take for this end to experience that change? And what is the shape of it? Well, I'm not going to talk about that because this is not a double E class. Okay, electrical engineering. Okay, so electrical engineers actually have to figure out the math behind all of this, and that is the reason why electrical engineers actually need calc 1, 2, 3, differential equations, and a few more things in order to model circuits like this. Okay, but to us, we'll just say that, yeah, that's a delay. Okay, we simplify things to just the logical level. It's like, yeah, it's going to take some time. That's all we need. So that means going back here, okay, going back to this picture here, the moment you make a change to any one of the two inputs, it's going to take a while before the output of the NAND gates change accordingly. Is that okay? So that amount of time is called the propagational delay. Okay, so that term, propagational delay, is very important every time we deal with anything that is electronic. So when you buy memory for your computer, okay, so let's just say that your desktop computer came with 8 gigs of memory, and because you're using Windows and you just upgraded from Windows 10 to Windows 11, Windows goes like, nope, not gonna install because you don't have enough RAM. They go like, ah, darn it. So you go purchase more RAM, right? So when you purchase RAM, other than the capacity, which is, oh, I need two sticks, each one has 16 gigs, okay, which is the capacity. What else do you need to take into consideration when you buy just RAM for your computer? The clock speed, right? So what determines the clock speed? Propagational delay. So propagational delay is eventually determining how fast your stick, your memory chip, or DIMMs, DIMMs, dual inline memory module, how fast your memory can change, and therefore it determines what is the throughput. Okay, so the megahertz of the clock speed for rating memory chips has to do with propagational delay. Okay, so this is actually important stuff. But from our perspective, we just go like, yeah, it takes a little bit of time before the output changes according to the input. It usually is measured in nanoseconds. So it's a really short amount of time, but nonetheless, it is not zero. The whole point is it is a small amount of time, non-zero. All right. Okay. Now it turns out that a lot of circuits work only because there's a propagational delay. Without a propagational delay, a lot of circuits actually would not work. All right, so in this case, okay, so let's just say that let me see if I can add a layer, because if I can add a layer, I can then reuse the same picture later, or I can do something like this. Okay, this is also something I can do. I can lasso this template, go to a new page altogether, and then just paste it here. But I forgot to copy first. Okay, that was my fault. All right, try it one more time. Lasso tool, and then copy. There we go. Now we can paste. There we go. Okay, so this is the circuit. And what we'll do, you guys have a question for me? You're good? Okay. So what we'll do is we'll say we have no idea what the current state is for the for both of the NAND gates. We don't know what it's outputting. Okay, we'll just say that we don't know. The only thing we know is we simultaneously change S to a 0, and also we change R to a 0. That is what we're changing. Okay, in other words, you're taking a wire that connects to ground, and you go like, I'm sticking this here and also here. Okay, so now the question is, what is the next thing that's going to happen? So the next thing that's going to happen is what I would call a NC, which is the abbreviation of node connectivity. Okay, so because of node connectivity, we now can say, oh, okay, because of this, we can say that n1 dot in bracket 0 would also be a 0, and 2 dot in bracket 1 would also be a 0. So now would be good time to explain what is this? I didn't know that this is a object-oriented programming class with arrays involved. No, no, this is just my notation, okay? So the notation of n1, okay, that's referring to the gate that we are looking at. N1 is the name of the gate. Dot in means we are referring to one of the inputs, but because there are two inputs, so I look at the two inputs as an array, and therefore I use array indexing to specify which one we are looking at. 0 is the top one, 1 is the bottom one. So are we good with the notation? Okay, so what is node connectivity? A node in electrical engineering and anything that has to do with circuit really just has to do with, oh, so you're talking about wire, okay? You're talking about the copper stuff, on a circuit board, okay? Electrically, this input pin connect to this input port of N1. Electrically speaking, this input pin connects to the second port of the input of N2. That is node connectivity. Are we good so far with what is a node? And because of node connectivity, if you change the state of the input pin, it's going to change the input port of the corresponding components. It's just because of how the wires are hooked up. We good so far? Okay. Okay, so this part is not difficult to understand. It's like, okay, we get it. So now we look at this and go like, okay, so after a certain propagational delay, so after the node connectivity or ANSI, then we go like, okay, PD, which is propagation no delay. So after propagational delay, I want to know. So the thing is, I have just made changes to the input of N1 and N2 because the first input of N1 is now changed to 0 from whatever it was before. I have no idea what it was. The second input of N2 was also changed to a 0. I gave it some time. Okay, it's like, okay, take your time, update stuff, let the inductance and capacitance and and resistance do its own thing, and then now we have the right answer. So the question is, potentially N1 dot out and N2 dot out may be affected. Now, I use the word may because it kind of depends on what they were before and what the new state is. If they are the same, then we go like, yeah, that didn't change. But we didn't know what were the outputs of these two gates. So if we know what they are now, it would be a change. It would be considered as a change. So now the question is, can we determine that? Okay, so I'm going to put a question mark here initially, and then we can go back and change it if we know what state, what is the output of N1 and N2. So right here, if you just look at this circuit, most people go like, well, we still don't know because there are two inputs to each NAND gate. We only know about one of the two inputs for each one of the NAND gate, so we don't have enough information to deduce what the output of each NAND gate is going to be. That would be reasonable reasoning. Okay, I know that is a very unreasonable thing to say about reasoning. But you get the idea, right? It's like, okay, we don't have all the information that we need, but we did. We actually did have all the information that we need because of the truth table. I know you don't want to listen to I know you don't want to hear the phrase in the truth table again, but here we go. It is the truth table. Dang it. Why is it so important in this class? So we look at the truth table of NAND. Okay, so you typically have XY as two independent input of a NAND gate. So we just say, okay, they can both be zeros. Y can be the one with the one. X can be the one with the one, or both of them can be ones. Okay, and now you look at, let's not even look at the circuit anymore. and we just look at this expression, okay? We have seen this already, okay, on day one of this class. So we go like, okay, so let's go ahead and fill in the table. X is 0, y is 0, the conjunction is going to be 0, but since we negate it, it is now a 1. X is a 0, y is a 1, so we have false and true. False and true is false, not false is true. This one is kind of just a kind of flipped version in a symmetric thing. So it is also a 1. And this is the only time we have a false because 1 and 1 is a 1, not 1 is a 0. Do you vaguely remember this? Okay, very good. So now we look at this table and go like, how can this help us in this situation? Well, one thing we notice, and it should not be surprising because of the name NAND, is, hey, if at least one side is a 0, the output is going to be a 1. Hmm? So it's only when both inputs are ones we know the output is a 0. But if at least one input is a 0, the output is a 1. Hmm? Nope, nope, not true. Correct. But S only goes to one NAND gate, R only goes to the other NAND gate. So that means from N1's perspective, you only know that one input is a 0. You still don't know what the other input is. And the same thing applies to N2. But my answer to that question is, why do you care? Yep, exactly. Because if at least one input of an AND gate is a 0, the output is going to be a 1. I don't care about the other input. So that means, oh, okay, so according to this, we can now say, we it's not unknown anymore. We actually know for sure that both NAND gates will output ones. Are we good so far? And then someone's going to observe this and go like, wait, Tech, because the output of N1 goes to the first input of N2, and then the output of N2 goes back to the second input of N1, that can potentially cause some changes. I go like, yeah, it can. It can potentially cause some changes. So now we go like, okay, another NC, okay, because of node connectivity, because of this output is electrically connected to this input. This output is also electrically connected to this input. So that's an NC, okay? It's a change due to node connectivity. So the result of this NC is, oh, okay, fine. We now know that N1 dot in square bracket 1, which is the second input of N1, we now know that it's going to be a 1. Does that make sense? And also at the same time, we know that N2 dot in bracket 0 is also going to be a 1. In other words, oh, okay, so the N1 and N2 as logic gates just experienced a change of its input. Okay, so that means, I'll give you some time. Okay, so we'll do a PD here so that the resistance, the capacitance, and the inductance are going to do their good thing and kind of delay stuff and whatnot. Okay, so after a certain amount of time, we go like, okay, so what is the output now? Well, nothing has changed. So I'm going to say no change here. Because at this point, what we know is this is still going to be a 0. This is now a 1. 0 NAND 1 is still a 1 based on the truth table. On the other side, this is now a 1. This is still a 0. 1 NAND 0 is still going to be a 1. But wait, that was the conclusion already. So that means we have a no change situation, which is also known as a steady state. So steady state. The circuit has stopped changing. At this point, from this point on, everything is now static. There's no change whatsoever in any way. Are we doing okay so far with the analysis up to this point? We good? All right. So what we're going to do next is to go like, okay, so we are going to take this whole picture here, and then we're going to say, what if I change one of the S or the R from a 0 to a 1? Okay, how is that going to impact the entire circuit? Okay, so we good with that? Okay, so let's go ahead and do it. And what I'll do is I'm going to just kind of designate these things over here. Okay, that's a 0, that's a 0, this is a 0, that's a 1, that's a 1, that's a 0. The outputs are both 1s. So that's why the outputs are both 1s at this point. Okay, so this is the starting point of the next phase. Okay, so I will erase this. Okay, so if you need to go back to this picture, you just kind of look at the time and I'll double check that we are still recording, and we are. So you can just say that, okay, by 11:15, your tag erased a portion of the screen, and you can always just kind of screen capture before I erase, and so you have a whole picture. Okay, so now we go to the erasing tool, specify what I need to delete. And now we go like, okay, let's change one of the input pins. It doesn't really matter which one. We'll just go ahead and say, okay, the input pin S is now going from a 0 to a 1. So we have a rising edge on that particular pin. And then we'll see what happens next. All right. So the first thing we're going to do is to say, well, because of node connectivity NC, we also know that N1 dot in square bracket 0 is also going to change to a 1. Okay, and that's almost instantaneous. Okay, so for the purposes of this class, we can say, the wire is kind of instantaneous. But because we just changed, because this input pin was a 0, now it is a 1. So we go like, well, maybe in the process we're going to change the output of in 1. Okay, so we want to see, okay, after a certain propagational delay, are we going to observe a change of the output of N1? Okay, so now we go like, is that going to change? Because we change one of the input pins, we always have to kind of try to figure out, is that going to change the output? Sometimes it does not, but sometimes it does. Okay, so in this case, it does change because what we are looking at here, okay, because I didn't update these things here. So we have just updated these two because this is now a 1, this is also a 1. When both inputs of N1 are 1s, the output would change to a 0. So now we go like, nope, that is now a 0. And guess what? This goes from here to here. This is also now a 0. We good? So now we go back here and then we say, yeah, we did change the output of N1. It is now a 1. And then because of node connectivity, okay, wrap around. We now know that N2 dot in bracket 0 is changed also as a result. In other words, we're looking at this pin here. It is also changed to a 0, not a 1. Sorry, that was my bad. It's not a 1. It is a 0. Are we good so far? Okay. And then after a propagational delay, because we just changed the input of one of N2, and anytime you change the input of any gate, you have to wait for a propagational delay, and then you ask, is that going to change the output of this thing? Well, in this case, after a certain propagational delay, there's no change because it was a 1 already. Now it is still a 1. Changing the other input of N2 to a 0 does not change the output, which was a 1 already. So we don't have a change, which is also known as a steady state, which is good. Okay, we like steady states because that means the circuit has settled down and all the inputs and outputs are now known. Okay, so are we doing okay so far with this picture? All right, so we're gonna do one more thing. So the next thing we're gonna do, okay, is to circle this part, get rid of it, and then we are gonna say, well, let's go ahead and change R to a 1, 2. So then we go like R, oops, there we go. Ooh, no, 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 no. Still get rid of All right. Wrong tool. Mm, take all this. Okay, so now we also want to say, well, what about changing R from a 0 to a 1? So we're going to do it here. Okay, I'm just going to cross out this time, put it to a 1. So that means after a NC, N2 dot in bracket 0 will now be a 1, which means this is now a 1. Are we good so far? N2, right. Oh, yep, you're right. Okay, you are correct. Let me back. Now we can do it. Okay, change that to a 1. Thank you. So we change that to a 1, and okay, so we say this is n bracket 1, not bracket 0, so I'll fix that too. Okay, thank you. So since we did change one of the inputs of the gate, we have to give it a little bit of time, propagational delay, and then we say, okay, after a propagational delay, are we looking at any changes to the output for N2? N1 is not a problem because none of the input of N1 is changing. So we only have to ask, what about N2? Is that going to change in any way? Nope, there's no change here. There's no change because we still have this input being a 0. So even though this input changed from 0 to a 1, the output continues to be a 1. Is that okay? So once again, we have a steady state. Okay, so are we okay with this progress? Let me summarize. Okay, so I'm going to summarize this in another table. So we'll use another page. So we look at S, R, Q, and NQ. NQ stands for not Q. Okay, it's the negation of Q. So the whole experiment started with, okay, assuming we know nothing about the circuit or the current state of the circuit, we change the inputs to all zeros, and then the conclusion is both outputs would become ones. And then we go like, okay, let's change S from 0 to a 1, let R remain to be a 0, and the end result of this is NQ continues to be a 1, but Q became a 0. So this is the output. Was that correct? Okay. And then we decided, let's make both S and R ones, and then the result is, oof, there's no change. Everything stayed the same as before. So that was the sequence that we went through. Okay. So let me give you, this is one sequence. So let me ask you, what if we modify the sequence just a little bit? Okay. This time we still start with 0, 0, but the next transition is opposite to what we did. In other words, we change R from 0 to a 1 first. And what do you think is going to happen to the output? Hmm? 1, 0. How can we do this without going through all that simulation again? Because the circuit is symmetric. Okay? In other words, if you go back to the circuit and you draw a horizontal line, kind of like this, okay, you will find that it is symmetric. The top half and the bottom half look exactly the same. So that means if we just change the sequence of which one is the R and which one is the S, well, the output is just going to be flipped, exactly opposite. Is that okay? All right. So why is that important? It is important because now if I ask you, what happens when both inputs are ones? In other words, we make a transition so that we now have 1, 1. What do you think is the output? It will still be 1, 0. Hmm, this circuit behaves a little bit strange. Why is it strange? because before this class, before we introduce the SR latch circuit, the output of a circuit only depends on the state of the input. Okay, we observed that in not only the NAND gate, a single NAND gate, we observed it in the a combination of NAND gates to make an AND gate. We observed that when we combine a bunch of NAND gates into a OR gate. We observed that when we combine a bunch of AND exclusive OR gates into the half adder and stuff like that, the input would completely determine the output. If I give you the input, you already know what the output would look like. But in this case, that is not the case. Because when the inputs are one ones, it is simply retaining the state from before. Okay, so I'm going to pause here and see if we are all grasping that concept that when the input S and R are both ones, we're simply saying to the circuit is like, whatever you were before, just keep that. Don't change anything. Is that okay? That is the simplest memory circuit in a computer. It's latching. Exactly. This is why it's called the SR latch, because it's latching the previous state and go like, okay, when it's a zero, you're changing the state, but when both inputs are ones, all you're saying is, okay, I'm not changing anything, just keep the current state. Whatever there was, keep it. Is that okay? All right. So are there any questions about the process by which we analyzed the circuit? No questions? All right. So let's go back because this goes like, okay, but what if what if we skip the middle step here and we just go straight from 0, 0 to 1, 1? What is going to happen then? I think that would be a reasonable question to ask, right? Because both of these sequences have something in between the 0, 0 and the 1, 1 input. So what if we skip that? What if we go straight from 0, 0 to 1, 1? So let's go ahead and simulate that particular transition, and we'll try to see what's going to happen. So what I'll do is I'm going to go back to the slide where we have the circuit. And this time we'll just kind of do a faster analysis. Okay, so we'll go ahead and select this, okay, using the lasso tool, copy, and go to the last page. We're going to use a new page here, and then paste it here. All right, move it up a little bit. All right, so that's all we need. I'm gonna change the states here. So we start with 0, 0 again. Okay. All right. One more. One more. There we go. All right. So get the wire back in. Okay. All right. So this time I'm going to only use a line, kind of like a trace here. Okay. So we have S R. We have N1 dot in bracket 0, N1 dot in bracket 1, N2 dot in bracket 0, N2 dot in bracket 1. Uh-oh, what did I do? Oh, maybe, because I was thinking, oh, what did I do? Okay, so N1 dot out, N2 dot out. Okay, so with all of these, as columns, in this case, I'm just going to use a way to indicate which ones are connected to which other one just by saying, oh, okay, S is connected to the first input of N1, R is connected to the second input of N2, which is up here, and then the N1 dot in1 is connected to the output of N2. So I'm just using these to kind of indicate the node connectivity. So this one connects to this one over here, but there's one more. Oh, I didn't specify the Q and the NQ, but that's really not super duper important in this particular simulation. All right, so we start with, okay, this is still the initial state, and the NC cycle, NC cycle is going to say, oh, because of the node connectivity, this is going to be a 0, and because of the node connectivity, this is also going to be a 0. And then we go for PD, okay, propagational delay. So after a certain propagational delay, the output of N1 is going to change to a 1. The output of N2 also changes to a 1. Are we good so far? And then we go for another NC here, okay? So the NC looks at the node connectivity. Oh, N1 output connects to N2.in.0. So that means if this is now changed to a 1, N2.out goes to N1.in bracket 1, but that's also changed to a 1. Are we good with this? Yes? That's just because of node connectivity. So now we go for another PD. Okay, because every time you change the input of something, you have to go for a PD, and yeah, it's not going to change anything anymore because at this point, um, this input of 0 still guarantees the output is a 1. This input of 0 still guarantees the output of that one being a 1. So we have a steady state. So we go like, okay, so are we good so far with this analysis up to this point? Okay. So now we go like, okay, we are going to change both input pins to 1s. So S is changed to a 1, R is changed to a 1. So this begins the next NC cycle. So when both are changed to a 1 because of node connectivity, so we now know, oh, okay, this is becoming a 1, and this one is also becoming a 1. We good so far? And then we go for another PD because this is the change of one of the input pins. This is the change of one of the input pins. So now we have to go after a PD. We look at the output of N1 and N2. We go like, oh, okay, I see N1 is going to output a 0. N2 is also going to output a 0. Where did my 0 go? It just took a while to update. That's fine. Okay. So both of those are zeros. Because of the propagation delay, what comes next? NC. So this 0, because of the node connectivity, goes back here. So this is now a 0. This 0, because of node connectivity, goes back here, which means this is also a 0. So what do we have at this point? What we have at this point is it has never happened like this before. I have no idea why it is doing this, but at least we still have the content. So at this point of time, we can see that N1 dot in bracket 1 is now a 0, which means after a certain propagational delay, okay, so we'll do one more row. This is a PD. So after a certain propagational delay, the output of N1 is going to become a 1, and then the output of N2 would also become a 1 because it is in a very similar situation. Because um, with N2, one of the input is now a 0, so that's why the output becomes a 1. Okay, you look at this and go like, that is kind of curious because it looks like we are repeating a loop here. And you're right, we are repeating a loop here. So at this point, the next NC and PD cycle will basically change the output of both NAND gates back to 0, 0, and then back to 1, 1, and then back to 0, 0. Now we do not have a steady state. This particular configuration of the circuit will never arrive at a steady state. It is now becoming an oscillator. The output would basically just alternate between 0, 0 and 1, 1 for eternity. Are we doing okay so far with this type of trace using a table, which can easily be done using a spreadsheet? So we're okay with this? All right. So I need to double check and make sure because this is what the lab looks like for today. So let me go into the lab of today just a little bit so that you can see what we are going to do. But before I switch the screen, let me just make sure that you guys, have captured all the notes that you want to capture. So we're good. All right. Okay. All right. So we're going to switch to the notes here because this is actually important too, because what I have just described is how do we keep track of changes within the circuit where there seems to be some kind of a loop. So if I were to go to this one, you can see that it's a really short module, but it described exactly what we just did. Okay, a lot of words, yes, but it does describe what we just did. So now we go back to our lab today, which is a somewhat involving lab. Okay, so I have to admit that this is kind of a longer lab. And the first thing we need to do is to change all these times, dates, and whatnot. Today is September 24th, and we are going to have it open at, or closed at 1:20 p.m. And I can open it like right away, 1:20 p.m. And okay, there we go. And this is a slightly different user interface. I have to go to loading. There we go. All right. So this homework assignment starts with copying a Google Sheet. Okay. So you go to this Google Sheet. Okay. So let me just go there. Oh, it just wants to edit. No, this is not what I want to do. Okay. I just want to follow the link. Just use this icon, right click, and then click open. Can I open it? Nope. I cannot open it. That is. Mm, okay, let me try this. Okay, this is right click, and it doesn't give me. Huh? Say again? Mm, nope. Okay, I know how to get this to work, but it's really a little bit more work because I can always go here, go to link options, copy the actual link itself, open a new tab, and then paste it back in. You don't have to do this, okay? Because when you view this, this is going to be, it will just be the way it is. So anyway, this is what you'll be looking at. Look at this and go like, what the? Okay. Well, I mean, there are a lot of things that are common between this and what we just did on on my tablet. So you would see input pin S, input pin R, the NAND gate of N1, the NAND gate of N1, N1, and then the NAND gate of N2, 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 output pin Q, and output pin NQ. So all the components are here. And then under NAND gate N1, there are three columns, in 0, in 1, and out. Under N2, there's also in 0, in 1, and also out. So that means the structure of this spreadsheet is essentially the same as what we just looked at on my tablet. Okay, Everything started off with a bunch of unknowns, okay, because we are just coming in and go like, we have no idea what is going on with this circuit before, and the only thing that we want to do first is to kind of change the input pins. Both S and R are changed from whatever it was, okay, which we don't know, to 0, 0, which is resembling what we have been doing in this class. Is that okay? So now you have to fill in the rest, okay? You have to fill in the rest of the NC, and then you have to go for the PD, NC, and then the PD. This one should be all blank by this time because we should have arrived a steady state at that point. And then we go like, okay, let's keep everything else exactly the same as before, but we are going to change the input pin R from a 0 to a 1 at this point, which is row 9. And then we'll figure out what is the NC going to do, what is the PD going to do, what is the NC going to do. So at this point, the PD should be all steady because there should be no more changes anymore. Okay, so in other words, I'm just using a table to capture what we have been doing using a picture. Yep. Yes. So only indicate when something has changed compared to what it was before. So what about row one and all the picture, all the colors? Okay. Well, I have a black and white tablet, so I cannot use colors. Okay, for one. Two, the colors are really just highlighting the nodes. In other words, it is basically telling you that N1 in 1, or the second input of N1, connects to N2 output, also connects to NQ port as an output pin. So the colors is really just a more visual way to tell you how things are connected. It is only useful in node connectivity. So that means column K, column I, and column E are connected together as one node. Column F, column J are basically is one node. Um, Column C, column H is one node, and then column B and column D is one node. Okay. Then what about row one? If the color is already telling us node connectivity, what is the purpose of node ID? Well, because I'm not colorblind, so if somebody is colorblind, the color that I have chosen may not work well for that individual. So that's why I also use integers or natural numbers to specify this is node 0. Okay, anything that is under node 0 are electrically connected. This is node 1, okay? Under anything that is in node 1 are electrically connected. This is node 2. Everything in node 2 are electrically connected, and the same thing for node 3. So it is really just a separate way or different way to indicate the connectivity between the ports of the components. Is that okay? But otherwise, this is the setup, okay? So the first thing you need to do is to make a copy of this spreadsheet, which is essentially open this, go to File, go to make a copy, but then you have to be careful because if you don't do anything, because most people just go straight to the button and say make a copy. That is not going to work because if you just click make a copy, the folder is not changed. So you'll be in a read only folder from your perspective. So what you will need to do is to go to the folder and change it to your own Google Drive first. Okay, because if you don't do that, then it will try to create the copy or the new file in the folder that you do not have write access to. All right, so this is kind of an important step. The rest is kind of up to you. It's you can choose however you want to do that part, but you do have to turn this in the form of sharing the document with me. Okay, so that's and also include a link to the document, but that part is actually fully explained in the lab too. This lab, I'm going to give you guys more time. In fact, I'm going to turn off the, let me go to settings. So I will not enable IP filtering because you might need more time to do this. So let me just go ahead and return. And I'm going to change the end time for this lab because potentially you might need more than the lab duration. It really depends on whether you understand what we have been doing in this class. If conceptually you already know what we are doing in this class and you have been taking notes and stuff like that, it should not take you too long. On the other hand, if this is all new to you and you're kind of like, I'm not really sure, I'm capturing all the ideas, then it might take you a little bit longer. So I'm going back to this lab. Oh, wrong. Oh, no, back. So I'm going to go back to this lab here. And there's a companion for you to turn in, quote unquote, turn in your sheet. This part, well, I might as well just make it in both cases. So make it visible, go to edit again. No, not that. Assign to, there we go. So I will give you the end of today to get this done. Just so that everybody do not have a lot of pressure to get it done really quick, because when you are working on this under pressure, you may not be learning everything that you kind of need to learn from this experience. So I'm just going to give you the end of today. I think most people can get it done within the lab session, okay? But just in case. This is the second component to today's lab, which is really just a submission interface. So I'm going to let you guys turn this in also at the end of today. So we'll say this is September 24th. This is 11:59 p.m. September 24th, 11:59 p.m. There we go. Save and publish. So the only thing left that you need to know is the passcode or the access code of the quote unquote quiz portion. So let me go to that one. Some of you might have seen it and go like, oh, okay, I remember what I saw earlier, but I will double check to make sure that everybody know the access code. Or maybe it doesn't even have an access code. Oh, it does actually. I have to go to build first. All right. Go to settings. Oh, somebody is already trying it. Step master. Because we are doing the whole thing step by step. So you might need to write this down in case you need more time than the lab session. Then you probably want to write down step master so that you can continue to work on this after the lab session. So step master, which I am sure is a trademark of some kind. Hmm? Is it Nintendo? I thought this is an exercise equipment. Or Disney. Well, I did cancel my, Disney Plus subscription. Well, they don't have anything that is of interest to me anymore, so might as well save 20 something bucks a month. Yeah, because it's Disney and then Hulu, and then for whatever strange reason they want to package everything with ESPN. I don't even watch sports of any kind, so it's like, why? So just cancel the whole thing. All right, so let me stop the recording and then upload it.